Slotted Aloha tried to improve upon the performance of pure Aloha. As we will see, it nearly doubles the throughput. The way it does is by dividing the time into discrete slots, and each slot interval corresponds to a frame time. And it places this restriction, which is crucial, in that it specifies that node can transmit frames only at beginning of slots. So naturally this assumes that nodes need to be time synchronized so that they know when that slot begins. So this picture shows that. So even when, for example, an arrival has happened here, you have to wait till the beginning of the slot before you can transmit that particular frame. And in this particular case, a collision happens when you have more than one transmission in a given slot. So what is this rule that a node cannot transmit in the middle of a slot? It has to wait for the beginning of the next slot to transmit. What is it achieving? So this rule basically prevents collisions with ongoing transmissions. In pure Aloha, if a packet came here, you would have transmitted, and if there was some transmission going on at that time, you would collide with it. Here, by insisting, you're at least ensuring that new attempts are not made in the middle of a slot, thereby not disrupting the transmissions that are happening in that particular slot. So this picture was for pure Aloha, but if same logic were to be applied to slotted Aloha, what do you think the vulnerability period is for slotted Aloha? So that's right, the vulnerability period reduces by half. Earlier it was 2 frame times, now it has become only 1 frame time. In other words, when you are attempting a transmission in this particular slot, you do not want any arrivals to have happened in this particular slot. And the probability of no arrivals, the previous slot, is given by this, thereby that is the probability of a frame being successful in a current slot is equal to the probability that no arrivals happen in the previous slot, that is equal to e to power of minus g. Thereby your throughput now is g e to power of minus g. Again, this is a function that varies with g, and the maximum value this function takes is when g is equal to 1 and the maximum value is equal to this, which is 36.8%. So at g is equal to 1, the number of empty slots is 37%. How did we get it? So this is basically the probability that no attempts were made in a given slot, that is probability of no arrivals in the slot, which is e to power of minus g with g set equal to 1. The probability of success in a given slot is if no arrivals happened in the previous slot. That is also probability e to power of minus g, thereby it is 37%. And the probability of collision is nothing but 1 minus sum of these both, that is equal to 26%. So any slot can be empty, or there is a successful transmission, or there is a collision. Ideally, you want more number of successful transmissions and lesser number of collisions as well as empty slots. Now, as the value of g increases, basically what this means is your empty slots decrease, but your collisions are going to increase exponentially. So that is what you see here, where this is S versus G, and as G is increasing, your throughput significantly falls down. And the maximum is achieved when G is equal to 1. So slotted Aloha is definitely better than pure Aloha, but still it is not a very good protocol because your utilization is very low. You're hardly utilizing 38% of your channel capacity. So all this poison business was confusing. So let's look at another method to analyze slotted Aloha. So here we are going to assume that there are n nodes with many frames to send. In other words, each node always has a frame to send in a given slot, and that a node transmits with probability p in a slot. Now given this, what is the probability that a node is going to experience a success, in other words transmit its frame without collision in a given slot? Calculate that. That's right, this probability turns out to be this, because you'd want the remaining n-1 nodes to not transmit in the slot and for you to transmit. So this is given by this particular expression. Now, what is the probability that a slot is successful? In other words, that slot has done useful work in the form of transmission and did not experience any collision. That's right. This is given by the probability that any node succeeds, and since there are n nodes, you just multiply by the above term with n. So this is the probability that a slot is successful. As you can see, this is a function of both the number of nodes as well as the probability p. I'm going to represent this by ENP. Basically, this is capturing the efficiency of the particular protocol, because only slots that are successful is when you're doing useful work. So if you want to maximize efficiency, you want to find P such that this expression has the maximum value. Now what will P turn out to be in that particular case? Why don't you work it out? Basically, you have to do some differentiation, and if you solve it, it turns out that the value of P at which efficiency is maximum is equal to 1 over n. And it also makes intuitive sense. If there are n users, you want each to try at 1 over n so that everyone has a fair share. So for this value of P in this expression, what is the maximum efficiency going to be? Naturally, you see it is going to be a function of n. So let's take in the limit n tends to infinity. What will the maximum efficiency be? So this turns out equal to 1 over e, and this is what we have seen in the earlier analysis also. 1 over e is nothing but the 38%. So as you can see, there is more than one way to skin a cat, basically a popular expression that tells there's more than one way to get a job done. A word of caution here: whenever you try to do theoretical analysis, the assumptions are very important. If you don't make the right kind of assumptions, your reality through implementation is going to be very different from what the theory says. In our example, we made many assumptions. We assumed Poisson arrivals, which is not true in practice. We assumed fixed packet sizes. This is also not true. You have different packet sizes. And I also assumed infinite population, which is again not true. Not specific to these protocols, but often you make assumptions about buffering, slotting, even when the system is not slotted, because this tends to easy analysis. If your assumptions are way off, your theoretical analysis will be way off from reality, and that is not what you should be doing. But if you make some reasonable assumptions, they may not be true, but they are slightly similar, then your analysis will give you very good insight into the operation of the protocol. Thereby you can improve it further, or you can address any corner cases that you have missed as part of the design. So to summarize, in this video, we looked at two very simple random access protocols, pure Aloha and slotted Aloha, and we saw how such protocols can be theoretically evaluated, and this analysis is a useful tool to know. And we saw that the efficiency of these protocols is rather poor. So going forward, we will look at some popular link layer technologies like Ethernet, and we will also look at their corresponding MACs and see how they improve their performance over Aloha.